The cold bit through flight suits like a living thing. 23 degrees below zero on the flight line at Grand Forks Air Force Base, North Dakota. December 1975. The tarmac stretched out in crystalline sheets of ice beneath sodium vapor lights that turned the pre-dawn darkness into industrial amber. Breath crystallized instantly in the air. The sound of idling jet engines created a low, thrumming pulse that resonated in chest cavities, a mechanical heartbeat for the machines that dominated the concrete expanse. Simultaneously, 4,000 miles east, warm air circulated through the analysis chambers of the Central Intelligence Agency's Office of Scientific Intelligence in Langley, Virginia. Fluorescent lights hummed steadily overhead. Analysts sat in comfortable chairs before plotting tables covered in satellite imagery and technical specifications. Coffee steamed in ceramic mugs. The temperature held at a steady 72 degrees. They studied photographs of swept-wing interceptors, examining every rivet, every panel line, every exhaust nozzle with methodical precision. The object of their attention dominated their thoughts as completely as winter dominated North Dakota: the F-15 Eagle. The new American air superiority fighter had entered service just months earlier, and it represented mathematical certainty made manifest in titanium and aluminum. 2 Pratt & Whitney F-100 turbofan engines, each producing 25,000 pounds of thrust. A thrust-to-weight ratio approaching unity, even with full fuel and weapons load. A maximum speed exceeding Mach 2.5. A service ceiling above 60,000 feet. Advanced radar that could track targets at distances the previous generation couldn't even detect. The Eagle had crushed every performance metric established by its predecessors. It accelerated faster than the F-4 Phantom. It climbed steeper than the F-106 Delta Dart. It turned tighter than the F-104 Starfighter. In the carefully calculated assessments produced by the Pentagon and validated by the intelligence community, the F-15 represented an insurmountable advantage. Soviet interceptors, the MiG-23, the Su-15, even the mysterious MiG-25 Foxbat, operated within fundamentally different performance envelopes. The mathematics were clear. The physics were undeniable. American air superiority seemed not just probable but inevitable. CIA analysts had calculated every scenario. They knew Soviet engine specifications. They understood Soviet metallurgy limitations. They had assessed Soviet aerodynamic theory. The numbers told a consistent story. The F-15 outmatched anything in the Soviet inventory by margins that couldn't be overcome through pilot skill or tactical innovation. 20% more thrust, 30% better thrust to weight. Advanced avionics that provided situational awareness Soviet pilots couldn't approach. The technological gap appeared unbridgeable. The Eagle represented more than just superior engineering. It embodied a philosophical approach to air combat refined through painful lessons learned in Vietnam's skies. Energy maneuverability theory, developed by Air Force Colonel John Boyd and mathematician Thomas Christie, provided the theoretical foundation. The idea was elegant in its simplicity. The fighter that could gain and lose energy most efficiently, through acceleration, deceleration, and maneuvering, would dominate any engagement. The F-15's power and aerodynamics gave it energy advantages that seemed mathematically insurmountable. On that frozen December morning in North Dakota, ground crews prepared Eagles for routine training missions. Standard procedures, standard configurations. The aircraft carried full avionics suites, complete weapons systems, all operational equipment necessary for combat readiness. They were formidable machines, but they were also complete systems, designed to fulfill multiple roles across diverse scenarios. Every pound of equipment served a purpose. Every system contributed to combat capability. But reports were beginning to arrive. They came through official channels first. The Fédération Aéronautique Internationale, the international body that governed and certified aviation records, processed submissions from unexpected sources. Time to climb records, Altitude records, speed to altitude records. The submissions came from Soviet test facilities, Podmoskovia, Zhukovsky, remote airfields in the southern USSR where experimental programs operated beyond Western observation. The first record appeared in official FAI logs on December 7th. Time to 15,000 meters, 2 minutes, 34.2 seconds. The number seemed impossible. The existing record, held by an F-4 Phantom, stood at 2 minutes, 51 seconds. The Soviet submission claimed a 17-second improvement. 17 seconds represented an eternity in high-performance aviation. It suggested thrust levels that didn't match known Soviet engine specifications. Analysts in Langley received the notification via encrypted teletype. They checked the numbers 3 times. Someone had made an error. Equipment malfunction. Measurement irregularity. The physical calculations didn't support the claimed performance. Soviet engines, the R-15B-300 turbojets, known to power the MiG-25, produced roughly 24,000 pounds of thrust each. The MiG-25, according to carefully accumulated intelligence, weighed approximately 80,000 pounds fueled and armed. The resulting thrust-to-weight ratio approached 0.6 to 1. Respectable, powerful, but not record-shattering. Before they could complete their verification procedures, a second record arrived. Time to 20,000 meters, 3 minutes, 12.6 seconds. The previous record, 3 minutes, 42 seconds. Another impossible improvement. The MiG-25 had taken a standing record and demolished it by 30 seconds. Then a third. Time to 25,000 meters, 4 minutes, 3.86 seconds. The precision of the measurement itself suggested sophisticated instrumentation and careful documentation. This wasn't estimation. This was exact timing validated through multiple independent systems. The reports accelerated. Time to 30,000 meters, 4 minutes, 31.7 seconds. Speed over a 500-kilometer course, 2,900 kilometers per hour. Altitude in horizontal flight, 37,650 meters, more than 23 miles high. Soviet test pilots were systematically destroying every time-to-climb record in the FAI registry. Records that had stood for years fell in days. The pattern suggested deliberate methodology, not random achievement. Someone had decided to claim supremacy across the entire performance spectrum, and they possessed the capability to execute that decision. At Langley, confusion hardened into focused investigation. The Office of Scientific Intelligence convened specialists from across the intelligence community: propulsion engineers, aerodynamicists, photographic analysts, signals intelligence experts. They gathered the complete intelligence file on the MiG-25 and began systematic analysis. The physics didn't cooperate. Every calculation returned the same conclusion: impossible. The claimed performance required either dramatically more thrust or dramatically less weight. Intelligence assessments firmly established Soviet turbine metallurgy limitations. The R-15B-300 engines used steel compressor stages because Soviet titanium production couldn't meet the demands of high-temperature turbine applications. Steel meant weight. Weight meant limits. The engines couldn't produce significantly more thrust without fundamental redesign requiring years of development. Could the Soviets have developed a new engine in complete secrecy? The intelligence apparatus considered the possibility. Satellites watched every major Soviet aerospace facility. Signals intelligence monitored communications between design bureaus and production plants. Human intelligence assets tracked personnel movements and resource allocations. No evidence suggested a crash program to develop revolutionary propulsion systems. The R-15B-300 remained the only engine that matched the MiG-25's configuration requirements. If thrust hadn't increased, weight must have decreased. But how? The MiG-25 was already a relatively simple design compared to Western fighters. It used steel in primary structures instead of titanium or aluminum, accepting weight penalties in exchange for high-temperature capability at sustained high speeds. The aircraft's mission, high-altitude interception of strategic bombers and reconnaissance aircraft, demanded long-range radar, heavy missiles, substantial fuel capacity. Stripping equipment would compromise mission effectiveness. The investigation expanded. Reconnaissance satellites repositioned to maximize coverage of known test facilities. Photographic intelligence from ground-based sources received renewed priority. An SR-71 Blackbird reconnaissance mission overflew Soviet airspace at the edge of radar coverage, capturing high-resolution imagery of Zhukovsky airfield during a brief window of opportunity. The photographs arrived in Langley 48 hours later. Analysts placed them under stereoscopic magnifiers and began the meticulous process of extracting every detail the film could yield. They examined airframe configurations, seeking evidence of modifications. They measured dimensions, comparing proportions to established MiG-25 specifications. They analyzed panel lines and access doors, looking for changes that might suggest internal reconfiguration. One analyst noticed something peculiar about the aircraft's color. Standard MiG-25 interceptors appeared in grey-green camouflage schemes. The aircraft in these photographs showed bare metal, a distinctive silver-white appearance that suggested unpainted surfaces. The absence of paint was visible across large sections of the fuselage and wings. Paint weighed approximately 25 pounds on an aircraft the size of the MiG-25. 25 pounds was negligible on an 80,000-pound machine. It represented 0.03% of total weight. Removing paint couldn't explain the performance improvements, but it suggested a philosophy. If they removed paint, what else had they stripped away? Acoustic intelligence provided additional clues. Monitoring stations along the periphery of the Soviet Union recorded engine sounds during test flights. Specialists analyzed the audio signatures, comparing them to established profiles of R-15 B-300 engines at various power settings. The fundamental frequency matched. The harmonics matched. The engines screaming through the stratosphere above Soviet test ranges were R-15 B-300 turbojets, not some revolutionary new power plant. So the impossible performance came from standard engines. The realization focused the investigation into a narrower question: how much weight had been removed, and what had they sacrificed to achieve these numbers? The analysts understood the physical principles that governed every aspect of flight. A fighter aircraft ascending vertically fought three enemies: its own weight, atmospheric drag, and gravity's constant acceleration of 9.8 meters per second squared. Thrust provided the only force opposing these enemies. The relationship was elegantly simple: thrust minus drag minus weight equals mass times acceleration. Increase thrust or decrease weight, and acceleration increased proportionally. The MiG-25's R-15 B-300 engines produced 48,000 pounds of thrust combined at maximum power. But maximum power couldn't be sustained indefinitely. Turbine inlet temperatures at full afterburner approached the material limits of the engine's steel construction. Sustained operation at those temperatures measured in minutes before catastrophic failure became probable. Time to climb records required sustained maximum power throughout the ascent. The engines had to survive the full duration without failure. If thrust remained fixed at approximately 48,000 pounds and performance had improved by margins approaching 30%, weight must have decreased by similar proportions. 30% of 80,000 pounds, 24,000 pounds. The intelligence community was looking for 12 tons of missing equipment. They began listing possibilities. The RP-25 Smerch radar system, 800 pounds. The 4 R-40 air-to-air missiles carried for operational missions, 3,000 pounds. The weapons pylons and launch systems, 500 pounds. Internal fuel tank capacity, The MiG-25 carried 37,000 pounds of fuel fully loaded, but could fly with partial fuel states for short-duration missions. A picture emerged. Strip the radar, remove the missiles, delete the weapons systems, fly with minimum fuel, just enough to complete the record attempt with safety reserves. The weight reduction started to approach the necessary magnitude. But something else was happening in the photographs. The analysts returned to the high-resolution imagery with new analytical frameworks. They weren't looking for what was present. They were looking for what was absent. One photograph captured a MiG-25 taxiing at Zhukovsky during early morning light. The sun angle created shadows that revealed surface details with exceptional clarity. An analyst noticed that certain access panels appeared different from standard configurations. Panels that should have been flush showed slight depressions. Panels that should have been painted showed bare metal. The aircraft looked incomplete, as though it had been partially disassembled and never fully reassembled. Soviet test pilots were flying stripped aircraft to the absolute edge of their operational envelopes. They were removing every component not absolutely essential to keeping the aircraft flying and recording the attempt. They were gambling that the engines would survive long enough to complete the climb. They were betting their lives on the structural integrity of an aircraft stressed beyond its design parameters. The true nature of the achievement was becoming clear. This wasn't advanced technology. This was extreme commitment. The Soviets hadn't built a better fighter. They had reduced a fighter to its absolute minimum configuration and pushed it into performance regimes where single failures meant certain death. On July 25, 1976, test pilot Alexander Fedotov climbed into a specially modified MiG-25 at Zhukovsky Airfield for an attempt on the absolute altitude record. The aircraft, designated E-266M, represented the most extreme evolution of the record-breaking philosophy. Ground crews had stripped every component not directly necessary for the flight. The morning temperature, 22 degrees Celsius. Air pressure, 1,013 millibars. Conditions were optimal. Fedotov advanced both throttles to full military power. The R-15 B-300 engines spooled up with their characteristic howl, a sound that combined pure mechanical violence with precisely controlled combustion. He released brakes. The MiG-25 accelerated down the runway, gaining speed with the urgency of an aircraft that weighed thousands of pounds less than standard configurations. Rotation, liftoff, gear retraction. He selected full afterburner. The engine's exhaust plumes extended 30 feet behind the aircraft as raw fuel ignited in the afterburner chambers. Thrust increased to maximum. Acceleration pressed him into the ejection seat with building force. The aircraft climbed at an angle approaching vertical. Airspeed increased. Altitude accumulated. The flight plan called for a zoom climb profile, a sophisticated maneuver that converted kinetic energy into potential energy through precise aircraft control. He would accelerate to maximum sustainable speed in level flight, then rotate sharply upward, trading speed for altitude as the aircraft arced toward space. At 45,000 feet, he reached Mach 2.8. Speed stabilized. The altimeter showed 14,000 meters and climbing. He pulled back on the control column, rotating the nose 20 degrees above the horizon. The aircraft's momentum carried it upward, even as atmospheric drag began bleeding speed. 50,000 feet. Mach 2.5. The sky transitioned from blue to dark violet. Atmospheric pressure decreased with each 1,000 feet of altitude. The engines consumed oxygen from progressively thinner air. Thrust degraded as air density dropped. 60,000 feet. Mach 2.0. The aircraft was still climbing, but deceleration was evident in the airspeed indicator's steady unwinding. He maintained pitch attitude, holding the nose high as the MiG-25 converted velocity into vertical distance. 70,000 feet, Mach 1.5. The controls responded sluggishly in the thin air. Control surfaces that generated powerful forces at sea level barely affected the aircraft's trajectory at this altitude. He was approaching the Armstrong limit, the altitude at which atmospheric pressure dropped so low that water boiled at human body temperature. His pressure suit was the only barrier between his blood and the vacuum of near space. 80,000 feet, Mach 1.0. The engines struggled to sustain combustion in air that barely qualified as atmosphere. Compressor stages designed for sea-level air density drew in molecules so sparse that turbine efficiency collapsed. Thrust dropped to a fraction of rated power. Then, at 83,000 feet, the right engine failed. Not gradually, not with warning. The turbine temperature limit was exceeded and internal components failed catastrophically. The engine destroyed itself in an instant of metal fatigue and thermal stress. Exhaust gas temperature spiked, then dropped to zero. The engine was dead. Fedotov felt the asymmetric thrust through the control column. The aircraft yawed right as the left engine continued producing reduced thrust, while the right engine contributed nothing but dead weight. At 83,000 feet, with barely sufficient airspeed to maintain control, asymmetric thrust meant immediate life-threatening emergency. He was still climbing. Momentum carried the MiG-25 upward, even with one engine destroyed. 85,000 feet, 90,000. The aircraft was no longer flying. It was following a ballistic trajectory, an object in freefall's early stages, still rising but with acceleration trending negative. 95,000 feet. The apex approached. Velocity dropped below Mach 0.5. The aircraft hung in the void between air and space, supported by nothing but residual kinetic energy. The altimeter needle touched 123,520 feet, 37,650 meters, 23.3 miles above sea level, higher than human beings could survive unprotected, higher than conventional aircraft could operate, higher than seemed physically possible for a fighter designed for 12-mile-high interceptions. Then the aircraft began to fall, not a controlled descent, a ballistic drop. The single operating engine produced insufficient thrust to maintain altitude at this extreme height. The aircraft entered a shallow dive, accelerating downward under gravity's patient pull. Fedotov pushed the nose forward, trading altitude for airspeed. The aircraft fell through 90,000 feet, 80,000. Air density increased incrementally. The controls began responding again as airflow over the surfaces generated meaningful forces. He restarted the ignition sequence for the dead right engine. Starter engaged. Fuel flow established. Ignition. The turbine caught, coughed, then resumed operation at reduced power. Asymmetric thrust disappeared. He regained full control. 70,000 feet, 60,000. The MiG-25 descended into breathable atmosphere. He extended the dive, building speed to ensure both engines received sufficient airflow for sustained operation. At 40,000 feet, he leveled off. Both engines ran roughly, but within acceptable parameters. He turned toward Zhukovsky and began a long, gentle descent to landing. Ground crews swarmed the aircraft after landing. They documented the engine damage. The right R-15B-300 required complete replacement. Internal components showed heat damage consistent with sustained operation beyond rated temperature limits. The engine had survived just long enough to complete the mission before destroying itself. Fedotov had been flying on one engine through the upper atmosphere with no possibility of ejecting successfully from that altitude. But the record stood. 37,650 meters. The number entered the Fédération Aéronautique Internationale's official registry. No aircraft before or since has flown higher in sustained horizontal flight. The record remains unbroken 48 years later. At Langley, analysts absorbed the implications. The Soviets weren't just breaking records. They were flying aircraft to deliberate destruction in pursuit of those records. They were accepting catastrophic failure as probable outcome. The commitment level suggested something beyond routine competition. This was strategic messaging delivered through aerodynamic achievement. Intelligence assets intensified their focus. If the Soviets were willing to destroy aircraft for record attempts, what else had they modified? What other capabilities did these stripped machines possess? Most critically, how much weight had actually been removed? The answer arrived through multiple intelligence channels converging on a single conclusion. A technical manual section photographed by a human asset in Moscow. Acoustic signatures analyzed by the National Security Agency. Most significantly, detailed examination of a complete MiG-25 that arrived in Japan on September 6, 1976, piloted by defector Viktor Belenko. Belenko's aircraft wasn't a record-breaking variant. It was a standard interceptor configuration with full operational equipment. But its examination provided the baseline necessary to understand what had been removed from the record machines. Japanese and American technical teams disassembled the aircraft component by component, cataloging every system, weighing every part, documenting every aspect of its construction. The intelligence community compiled the complete modification manifest. The list was comprehensive. The list was devastating. The list explained everything. The RP-25 Smerch radar system, removed. 800 pounds deleted. The aircraft was blind beyond visual range. It couldn't detect targets. It couldn't guide missiles. It existed purely as a platform for engines and fuel. The 4 R-40 air-to-air missiles and their launch systems, removed. 3,500 pounds deleted. The aircraft couldn't engage enemies. It couldn't defend itself. It was defenseless against any threat. The auxiliary fuel tanks and associated plumbing, removed. 2,000 pounds deleted. Range collapsed to a fraction of operational requirements. The aircraft could fly for perhaps 40 minutes before fuel exhaustion forced landing. The radar warning receiver, removed. 40 pounds deleted. The pilot couldn't detect missile launches or targeting radars. He flew without awareness of threats. The radio compass and navigation systems, removed. 70 pounds deleted. The pilot navigated by ground references and timing. Clouds would make navigation impossible. The identification friend or foe transponder, removed. 25 pounds deleted. Soviet air defenses couldn't identify the aircraft electronically. It relied on pre-planned flight corridors to avoid being shot down by its own side. The air conditioning system, removed. 150 pounds deleted. Cockpit temperatures during high-speed flight would approach limits of human tolerance. The pilot endured rather than operated in comfort. The protective coatings and paint covering the entire airframe, removed. 130 pounds deleted. The bare metal skin offered no corrosion protection. The aircraft's service life measured in weeks rather than years. Numerous avionics boxes supporting systems no longer installed, removed. 300 pounds deleted. Empty equipment bays created void spaces throughout the fuselage. Internal armor protecting critical systems, removed. 200 pounds deleted. A single bullet or shrapnel fragment could destroy essential components. The emergency systems beyond the absolute minimum, removed. Redundant hydraulic pumps, backup electrical generators, secondary flight instruments, deleted in favor of single point of failure configurations that accepted catastrophic risk. Running total, 6,915 pounds removed. 3.5 tons of equipment stripped from an aircraft that weighed 80,000 pounds operationally configured. But they had gone further. The fuel load was reduced to mission requirements plus minimal reserves. A typical record attempt carried 18,000 pounds of fuel instead of the 37,000 pounds the aircraft could accommodate. 19,000 additional pounds deleted. Total weight reduction, 25,915 pounds. More than 13 tons. The modified MiG-25 weighed 54,085 pounds. The engines produced 48,000 pounds of thrust at maximum afterburner. When they divided thrust by weight, The result was 0.89 to 1. The number approached the magical threshold that fighter designers pursued but rarely achieved: unity. A thrust-to-weight ratio of 1 to 1 meant the aircraft could accelerate vertically, climbing straight up under thrust alone without depending on lift from wings. It meant energy maneuverability that transformed physics into advantage. The standard operational MiG-25 possessed a thrust-to-weight ratio of 0.6 to 1, respectable for an interceptor, adequate for its mission. The F-15 Eagle, which had triggered such confidence in American air superiority, achieved 0.9 to 1 when lightly loaded, close to unity but not quite there. The stripped record-breaking MiG-25 exceeded 0.85 to 1 consistently. Some variants approached 0.93 to 1. For the first time in aviation history, an operational fighter-derived aircraft had achieved thrust-to-weight ratios previously associated only with experimental rocket planes and missiles. The number explained every impossible record. The number explained the vertical climbs and the stratospheric altitudes. The number explained why Soviet test pilots could pour their stripped machines into the sky and watch them disappear into the violet reaches of the upper atmosphere. The mathematics were elegant and brutal. A 35% reduction in weight combined with unchanged thrust produced 54% improvement in thrust-to-weight ratio. That improvement manifested as 30-second reductions in time to climb records, as altitude ceilings 70% higher than operational configurations, as sustained acceleration profiles that American intelligence had calculated were physically impossible for Soviet technology. The F-15 Eagle, configured for combat with full avionics and weapons, still outperformed the operational MiG-25 in every meaningful combat metric. But the MiG-25, stripped to its skeleton and flown by pilots willing to accept catastrophic risk, had achieved performance levels no Western aircraft approached. The comparison was meaningless from a combat perspective. The record machines couldn't fight, couldn't navigate effectively, couldn't survive sustained operations. But the strategic message was clear. Soviet engineering could match or exceed American performance when freed from operational constraints. The revelation carried a deeper irony that intelligence historians would recognize only years later. The MiG-25's development traced back to 1964, when Soviet intelligence detected the American XB-70 Valkyrie bomber program. The Valkyrie was designed to penetrate Soviet airspace at Mach 3.0 at altitudes above 70,000 feet, speeds and heights that rendered existing Soviet interceptors useless. The Soviet response was the MiG-25 program, tasked with developing an interceptor capable of reaching and destroying the Valkyrie. Engineers at the Mikoyan Gurevich Design Bureau created an aircraft optimized for extreme speed and altitude. They accepted weight penalties from steel construction. They designed powerful but inefficient engines. They developed long-range missiles and radar systems capable of engaging bombers at the edge of the atmosphere. The MiG-25 emerged as exactly what was needed to counter the Valkyrie threat. Then, in February 1964, before the MiG-25 entered production, the XB-70 program was cancelled. Strategic bombers flying at Mach 3 were obsolete before deployment. The advent of surface-to-air missiles and the development of intercontinental ballistic missiles made high-altitude penetration suicidal. The American doctrine shifted toward low-altitude penetration, where radar coverage gaps provided survivability. The Valkyrie threat evaporated. But the MiG-25 program continued. Production facilities had been built, supply chains established, thousands of workers trained. The aircraft entered service in 1969 as a solution to a problem that no longer existed. Soviet planners adapted it to new roles: reconnaissance, high-altitude interception of strategic reconnaissance aircraft, air defense against cruise missiles. The supreme irony emerged only after Viktor Belenko's defection provided detailed intelligence. When American technical teams examined his aircraft, they discovered the truth about the system that had triggered such concern. The MiG-25 was crude by Western standards. vacuum tube electronics instead of solid-state systems, steel instead of titanium, welded construction instead of precision machining. The radar was powerful but indiscriminate. The missiles were heavy and unsophisticated. Top speed was indeed Mach 2.8, but sustained flight at that speed measured in minutes before engine damage became inevitable. The aircraft was a blunt instrument designed to catch and destroy a specific target. Against the XB-70, it would have been effective. Against modern fighters employing energy maneuverability tactics, it was nearly helpless. The F-15 Eagle, developed partially in response to intelligence about the MiG-25's capabilities, vastly exceeded the Soviet interceptor in combat utility. The Americans had built a Ferrari to counter what they feared was a Soviet Ferrari. When they finally examined the actual Soviet machine, they discovered it was a specialized drag racer, incredibly fast in straight lines, nearly uncontrollable in turns, effective only in its narrow design parameters. The comparison was simultaneously reassuring and embarrassing. But the Soviets had discovered something about their drag racer. When stripped of everything except engines and fuel, when flown by pilots willing to risk death at high altitude, when pushed beyond design limits with acceptance of catastrophic failures, the MiG-25 could achieve performance levels that made Western intelligence analysts question their understanding of physics. The records didn't make the MiG-25 a superior fighter. They made it a symbol of how far determined engineers and courageous pilots could push marginally superior thrust-to-weight ratios when freed from operational requirements. The Soviet response to the F-15's appearance demonstrated their unwillingness to concede any measure of supremacy. Beginning in 1975, as F-15s entered operational service with American squadrons, Soviet test organizations initiated crash programs to reclaim performance records. If American fighters represented a qualitative leap, Soviet record machines would demonstrate that raw performance still belonged to the USSR. The Americans eventually responded in kind. Beginning in 1977, modified F-15 aircraft designated Streak Eagle entered the record competition. The modifications followed the Soviet template: strip every component not essential to flight, remove radar, weapons systems, one of the two engines in early attempts, paint non-essential avionics, reduce fuel to mission requirements, accept risk, push pilots and aircraft to absolute limits. Streak Eagle reclaimed time-to-climb records across multiple altitude checkpoints. American test pilots matched and exceeded Soviet achievements using similar philosophy and comparable thrust-to-weight advantages. The competition continued through the late 1970s, each side iteratively stripping more weight and accepting greater risk in pursuit of numerical supremacy. But the records themselves became increasingly irrelevant to actual military capability. Operational fighters flew combat missions with full equipment loads. Real warfare demanded radar, missiles, fuel, defensive systems, armor, communications equipment. The stripped record machines represented propaganda tools more than military assets. They demonstrated engineering capability and pilot courage, but they contributed nothing to combat effectiveness. The MiG-25's true validation came not in record books, but in operational deployments. The interceptor entered service with Soviet air defense forces, where it provided high-altitude coverage against strategic reconnaissance aircraft. Export variants flew with Soviet client states, where they operated in conflicts across the Middle East and North Africa. The combat statistics told their own story. In engagements against Western aircraft during conflicts in the 1980s and early 90s, operational MiG-25s achieved modest success. The aircraft's speed allowed it to engage or disengage at will. Its altitude capability provided tactical flexibility, but its crude avionics and limited maneuverability made it vulnerable to modern fighters employing beyond visual range missiles and sophisticated electronic warfare. Against Israeli F-15s over Lebanon, MiG-25s were outmatched. The Eagle's combination of long-range radar, advanced missiles, and superior energy maneuverability dominated engagements. Syrian MiG-25 pilots learned to respect Israeli aircraft and avoid combat when possible. Speed and altitude provided escape, not victory. During the Gulf War in 1991, Iraqi MiG-25s flew limited missions against coalition aircraft. One Iraqi MiG-25 achieved the distinction of scoring the only aerial victory against a coalition aircraft, downing a US Navy F-18 Hornet with an R-40 missile. But losses were disproportionate. Coalition fighters destroyed multiple MiG-25s in air-to-air engagements. The interceptor's limitations were fully exposed against integrated air defense systems and modern fighters with fourth-generation avionics. The record-breaking variants never saw combat. They existed for a specific purpose, demonstrating Soviet capability through measurable achievement, and they fulfilled that purpose completely. Between 1973 and 1977, Soviet test pilots flying stripped MiG-25 variants set 29 world records certified by the Fédération Aéronautique Internationale. 29 times, they pushed aircraft and themselves into performance regimes that defied Western predictions. 29 times, they proved that determination and calculated risk could overcome technological disadvantages. Some of those records remain unbroken decades later. The absolute altitude record of 37,650 meters stands because no nation has since committed resources to breaking it. Modern fighters possess greater capability, but operational requirements demand equipment that adds weight. The era of stripped record machines ended as both superpowers recognized the propaganda value was finite and the risks were substantial. The final MiG-25 record variant, designated Year 266M, resides today at the Central Air Force Museum in Monino, Russia. The aircraft rests on static display, its bare metal skin still visible, access panels still marked with Cyrillic identification stencils. Visitors can stand beneath its wings and examine the machine that flew higher than any other fighter in human history. The engines are cold, the cockpit is empty, the record stands. The story of the MiG-25 record attempts crystallized a moment in Cold War technological competition when both sides pushed performance boundaries for strategic messaging purposes. The physics were real, the achievements were genuine, the risks were extraordinary. Soviet test pilots climbed into stripped aircraft, knowing that engine failures at extreme altitude meant probable death. American test pilots matched that commitment, accepting similar risks in pursuit of counter records. The mathematics that explained the impossible were elegant. Reduce weight by 35%. Maintain thrust at maximum sustainable levels. Accept that engines will destroy themselves. Accept that pilots will fly without essential systems. Accept that single failures mean catastrophic outcomes. The resulting thrust-to-weight ratio crosses the threshold where vertical acceleration becomes possible, where atmospheric limitations fade, where the edge of space becomes accessible to machines designed for combat at 12 miles altitude. The lesson transcended aviation. When capable engineers receive clear objectives and acceptance of risk, performance boundaries expand beyond conservative predictions. When pilots possess skill and courage sufficient to operate at the ragged edge of controllability, aircraft respond with achievements that appear impossible from safety-minded perspectives. When nations compete for symbolic supremacy, the measurements become precise and the commitment becomes absolute. The sky above Zhukovsky Airfield holds the memory of those climbs, the trace of exhaust trails long since dissipated, the echo of engines screaming at temperatures that melted internal components, the arc of trajectories that carried aircraft and pilots into the violet threshold between atmosphere and void. The numbers remain in record books, precise to fractions of seconds and single meters of altitude. The physics remain unchanged, thrust and weight in eternal opposition, with only the ratio between them determining who rises and who watches from below.